A very good morning to all. This is Dr. Manjunath Chennapugod from Anveshana Academy, Bangalore, India. Dear students, in the previous class we discussed about Carnot Cycle. Okay, the working principle of Carnot Cycle we discussed, and to calculate the Carnot efficiency we done one derivation also. What is the derivation? So that is we will discuss. Okay, so now today I will move towards next topic. Okay, so now what I will do, I will try to do some numericals on Carnot engine. Dear students, in the previous class we discussed, okay, and we derived an equation for Carnot efficiency. How to calculate Carnot efficiency? We have derived an equation, that is what Carnot efficiency is equal to 1 minus Q2 divided by Q1, or in terms of heat data, or this same thing we can calculate with the help of one more formula with the help of temperature data, that is Carnot efficiency is equal to 1 minus T2 divided by T1, where T1 represents temperature of heat source and T2 represents temperature of sink actually. Similarly, Q1 represents heat supplied, Q2 represent heat rejected in the sink. With the help of this formula, the equation, we can calculate the efficiency of the Carnot engine. This equation is derived by the Carnot that we have discussed in the previous class. Okay, so dear students, today I am going to solve some numericals on Carnot engine. Okay, so Carnot engine that we will do it today. Now, so first problem, I will read the problem first, then I will solve it step by step. Okay, problem number 1. So 0.5 kg of air, the two ideal gas, is telling perfectly. So it's telling clearly 0.5 kg of air, that is ideal gas, executes a Carnot power cycle having a thermal efficiency of 50%. The heat transfer to the air during isothermal expansion is 40 kilojoules. Okay, at the kilojoules. Okay, at the beginning of the isothermal expansion, the pressure is 7 bar and the volume is 0.12 meter cube. Okay, so this is the data he has given and is asking determine the first one, maximum and minimum temperature of the cycle in Kelvin. First determination. Second determination is asking to calculate the volume at the end of the isothermal expansion in meter cube. That is the second determination. Third determination is the heat transfer for each of the four processes in kilojoules. This is the problem he has given, dear students. Okay, so first step, what you have to do, you have to read the problem twice or thrice, try to understand very well. Once you understood, then you draw a rough sketch which is relevant to problem. Okay, so draw a particular problem, rough sketch of that particular problem and list out the given data, and if possible try to list out the important formula which are related to this problem. This is the first step you need to identify. So now what I will do, now I will try to analyze this problem first. Okay, after understanding the problem, try to analyze it. Now what are the things he has given? Yes, he has taken a heat engine. So for that heat engine he is supplying certain amount of mass of air that he has given, 0.5 kg of air he is going to supply. Then what type of cycle he is telling now? He is telling it is a Carnot cycle, because many cycles will come, dear students. Carnot will come, Otto will come, diesel will come, okay, Rankine cycle will come, Brayton cycle, like many cycles will come when it comes to gas power cycles. But here is clearly telling the problem is related to Carnot cycle. Hence, you have to identify the type of the cycle. It's a Carnot cycle. That's a fine. Then what all you need to do here now? He has given some data, thermal efficiency he has given. Some basic data he will give. And he will ask to something to find. So first he has given thermal efficiency, that to 50% he has given. Then now when he is transferring, then when he is going to supply heat to the engine, right, the transfer of heat he is telling now. So heat transfer is there, that also need to mark it. And when we are going to supply that ideal gas with certain heat, that is having certain amount of pressure, that pressure we can call it as a initial pressure, that notation we can give it as a P1. Okay, and that ideal gas having certain amount of volume, that volume we can call it as a initial volume. Initially it is having some volume, that we can call it as a initial volume, that we can represent it as a V1. Okay, these are some key parameters or key factors he has given in the problem. That's a fine. Okay, as I told, this problem is related to Carnot cycle now. So now when it comes to Carnot cycle, as I told, there are four important processes. Okay, so the four important processes, but here isothermal expansion process play a very important role. Now what actually you are doing here, now you are supplying certain amount of heat to the engine during isothermal expansion process, that we can call it as a heat absorption or heat addition. Because of that heat absorption or heat addition, we are going to get the work done. Okay, so now what we can do here, now with the help of thermal efficiency equation, with the help of all data we can calculate the thermal efficiency. We have to do the calculation of thermal efficiency. Then so to solve this numerical, as he told, he is using an ideal gas, then that ideal gas obeys the ideal gas equation. So that also we need to consider, that ideal gas equation or ideal gas law it is going to obey, that we need to consider to calculate the heat transfer or thermal efficiency or temperature or pressure, whatever it may be. So you have to mark all the key important parts into your small diagram. Okay, fine, you can draw this diagram better. Okay, as he is telling, there is a heat engine, so that is we can call it as a, that heat engine we can call it as a Carnot engine is there, or Carnot, it works on a Carnot cycle. Okay, fine. Now he is telling, now it is having a certain amount of mass, he is going to supply certain amount of mass to the engine, mass of perfect gas, that we can take air actually here 0.5 kg. Okay, 0.5 kg of air is going to supply to the engine, and is supplying at a certain heat actually. What is the heat actually? So he is telling Q1 is equal to 40 kilojoules. That heat mass of the air is supplied to the engine, and he is going to supply certain amount of heat to the engine, that heat is 40 kilojoules. Okay, and he is telling, now later you can see now on that the efficiency of that engine works only 50%, that he is telling now current efficiency works only 50%. He is telling, it is a numerical, it is a problem he has given this data, you need to do the calculations. Okay, fine. Now at the beginning of the isothermal expansion, at the beginning of, now when it comes to heat engine, right, it is going to have four processes. That is isothermal expansion, as I told. Second one, adiabatic expansion. Third one, isothermal compression. Fourth one, adiabatic compression. At the end of the isothermal expansion, he has given the pressure. The pressure of the air is 7 bar, that is nothing but what, P1, we can call it as a 7 bar he has given. The next, volume of the gas, that whatever he is supplying gas, right, ideal gas to the engine, right, it is having pressure 7 bar, and that volume of that gas is, we can call it as initial condition, so that we can take it as a 0.12 meter cube. This data he has given. Then what actually is asking now, this all data he has given to this particular Carnot engine, is asking to calculate first parameter, the maximum and minimum temperature. What is the maximum temperature? We know already, we can get maximum temperature at heat source, that is T1. You need to calculate what is T1. Next, minimum temperature. What is the minimum temperature? Minimum temperature we can get at sink side, okay, or heat waste heat reservoir, that is T2. Okay, fine. Next, he is asking to calculate the volume of the end of the isothermal expansion. Okay, beginning of the expansion he has given. Dear students, we have to read the sentence here now. Beginning of the isothermal expansion, he has given 0.12 meter cube and 7 bar. That is P1 and V1. But next he is asking end of the then he is asking here, what is the volume of the gas at the end of the isothermal expansion? That means what? I will tell. He is asking to calculate what is V2. V2 is equal to how much? With a PV diagram, I will tell you how it is V2, V1. I will tell again. Okay. Now, third one is asking to calculate the heat transfer at each pore process. That means what is asking to calculate heat transfer in process 1, that is we can call process 1 is equal to how much, heat transfer at adiabatic expansion is equal to how much, heat transfer at isothermal compression is equal to how much, heat transfer at adiabatic compression is equal to how much, is asking to calculate heat transfer during in all process. We need to calculate now. So now dear students, so based upon this based upon the given data, what we done, we analyzed the problem and we understood what we need to calculate. Okay, so now I will move towards next step. Dear students, you can see now, as he is telling, there are pore processes. What are the pore processes? When it comes to Carnot engine, you should be familiar with what? Pore processes here now. What are the pore processes that you can see here? Okay, so isothermal expansion, okay, adiabatic expansion, isothermal compression, adiabatic compression. But for this Carnot engine, he has given some initial condition, that also you need to mark, dear students. Now, so now you can see the PV diagram here now. So initial condition, the piston is going to start from expansion, that is isothermal expansion. This is the beginning and this is the end actually. So at beginning he has given some data. What is the pressure of the air? That is P1, that he has given in terms of 7 bar. Okay, then V1 he has given some value, he has given V1. What is the V1 he has given? That you can see here now. V1 he has given 0.12 meter cube. Beginning V1 is equal to 0.12 meter cube he has given. But he is asking to calculate the volume of the ideal gas at end of the isothermal expansion, where the isothermal expansion is going to end at point 2, dear students, that you can see here now. At 2, the isothermal expansion process is going to end here now. This is a point 2. So here he is asking to calculate the volume of the gas at end of the isothermal expansion, that is V2 is equal to how much. That is fine. Okay, now so now what you have to do then? This is what expansion from 1 to 2 isothermal expansion, then 2 to 3 is adiabatic expansion. These are two processes, expansion, 2 processes are compression. Again from 3 to 4, isothermal compression. Again 4 to 1 is adiabatic compression. These are 4 processes are very important to do the calculations here now. So first step, what you have to do here now? Here one thing you have to do. What is that? That you can see here now. Convert pressure to Pascal. So dear students, he has given P1 is equal to 7 bar he has given. But all data are there in Newton per meter square or in Newton or meter square. So for that purpose, you need to convert this bar into Newton per meter square. How to convert that bar into Newton per meter square? Dear students, already we know 1 bar is equal to 10 to the power of 5 Pascal. Okay, 10 to the power of 5 Pascal. And also we know that 1 Pascal is equal to 1 Newton per meter square. So therefore 1 bar I can express in terms of Newton per meter square is equal to 10 to the power of 5 Newton per meter square. So therefore 1 bar of pressure in terms of Newton per meter square or Pascal is 10 to the power of 5 Pascal or Newton per meter square. So convert that pressure to Pascal, because that is nothing but what, as I told, 1 Pascal is equal to 1 Newton per meter square. Hence why I am converting this part to Newton per meter square? To maintain the uniformity in the unit. So converted, fine. Then to do the calculations, as he is telling this is ideal gas. If it is ideal gas, it is going to obey the ideal gas law. Hence what you have to do? You have to apply the ideal gas law. Once you apply the ideal gas, then you will get some data. With help of that data, what you can do? You can calculate the efficiency. Once you done the calculation of efficiency, you can easily determine the volume at the end of the isothermal expansion, that is V2. Similarly, you can calculate with the help of all data. You can calculate the heat transfer at all process. Okay, this is about the numerical background. Now, how to solve this numerical, that you can see here, dear students. So now, once again in quick recall, what all things he has given? Mass he has given, Carnot cycle he has given, efficiency of that Carnot he has given, the heat supply during isothermal expansion he is given, initial pressure he has given, volume he has given. As I told, there are 4 processes that you can see here now. This is a Carnot engine. He is asking to calculate first one, maximum temperature and minimum temperature, and is asking to calculate the volume at the end of the isothermal expansion. Then is asking to calculate the heat transfer at all process. That you have to do it now. So the first step, calculate the maximum and minimum temperature. Then determine the volume at the end of the isothermal expansion. Later you calculate the heat transfer at all the process. How it is, that you can see here now. So I listed out the given data. 0.5, 50%, all things he has written. So processes are 1 and 2 here now. Isothermal expansion. So the same thing you can represent in TS diagram to know the temperature variations. That is T1 is equal to T2 is equal to TS, highest temperature. T3 is equal to T4 is equal to TL, that is the lowest temperature, that we have studied in the previous video. So QS represents heat supplied during process 1 to 2. Then heat rejection takes place at 3 to 4, that is QR. Okay, QS and QR. These are the data and PV diagram you can have. So now what I will do, we know I need to use the ideal gas equations to solve this numerical. How to use that you can see here now. What is the equation? PV is equal to mRT. Now I will apply this equation at a particular point 1. Okay, I will apply that ideal gas equation at a particular point 1. Then what will happen? P1 is equal to V1 is equal to M P1. Just a minute, it is not writing there. Okay, I will apply the point here. Okay, P1 is equal to mRT1. So that same equation I am using here. P1 is equal to V1 is equal to mRT1. So now here I need to calculate the T1. T1 is nothing but what? Highest temperature or temperature of the heat source, that I need to calculate. To calculate that, I can rearrange this equation. Now I can write now T1 is equal to P1 divided by V1 divided by mR. Okay, so now P1 V1 divided by mR now. So P1 V1 divided by mR, where R is the gas constant that we know already, 0.287 kilojoules per kg Kelvin. That is a constant you have to remember. And pressure is P1 is the pressure that must be in terms of what? Kilopascal. Okay, kilopascal. Because we are using joules, right? 1 joule is equal to what? Again, 1 joule is equal to 1 Newton meter. Hence, if it is in joules, to maintain the uniformity, I need to put a pressure in terms of Pascal or in Newton per meter square. So therefore, what I will do now? So T1 pressure, I am going to put it in terms of what? 7 into 10 to the power of 2. So the bar is converted into kilopascal. Okay, then into V1. What is the V1? He has already given, that is 0.12 meter cubes substituted, divided by what is the mass he has given? 0.5 kg he has given. Then what is the radial gas constant? That is 0.287. Substitute, you are going to get a temperature, that is 585.36 Kelvin. Because you are going to put ideal gas constant in terms of Kelvin, the final answer we are going to get in terms of what? Kelvin itself, that is T1 is equal to 585.36 Kelvin. Hence we determine the temperature of the heat source at beginning. Okay, that is T1. So now I need to calculate the minimum temperature. How to calculate the minimum temperature? That minimum temperature is T3. We know already, derived the equation. What is that equation? We already derived the equation. 1 minus T2 divided by T1. T2 is what? Lowest temperature hours. Okay. What is the efficiency of the Carnot engine? He has given 50%. That means what? 0.5 is equal to 1 minus T2. I don't know. Lowest temperature, I will keep it as it is. But T1 highest temperature, I already know. I calculated, that is 585. So I will put it here, 585.36 now. You can see at the left hand side and right hand side, the only unknown is T2. Substitute and you can get the value of what? T2. Okay, so lowest temperature. Some authors they will take T3 also. If you want, you can take a T3 also. So you, as per this now, 1, 2, 3. Here is the lowest temperature. You can take 1 minus T3 by 1 minus T3 by T1. Notation, however you can give. Okay, so now 1 minus T3 by, here according to this diagram, highest temperature is 1, lowest temperature is T3. So T1, so T3 by T1. So T3 by T1, do substitution, you will get the value here now. So 0.5 is equal to 1 minus T3 by 585.36. Then what will happen? Do substitution, you will get the value of what? T3. T3 is equal to 292.68 Kelvin. Hence you determine the temperature 2 also. The first parameter, you can go back and you can see. Okay, the first parameter, the maximum and minimum temperatures, that is T1 and T3 are calculated. T1 and T3 are calculated. Okay, fine. Now next second step is we need to calculate the volume at the end of the isothermal expansion. Then how to calculate that? We have again an equation now. So heat supplied equation we know already. That is what? P1 V1 ln of V2 by V1. So what is heat supplied? Amount of heat supplied during isothermal expansion he has given, that is 40 kilojoules he has given. That is 40 is equal to, what is P1? Again put it in terms of kilopascal, that is 7 into 10 to the power of 2 into V1 0.12. Then ln of V2 you don't know, keep it as it is, but you know the value of V1, substitute the value of V1. Then do substitution. Now here you can see at the left hand side and right hand side, you know all the data except V2. So that means what? By solving this equation I can get the value of what? V2. Now so therefore what we can do, I will take this term out. Just a minute. Okay, so now what I will do, I will take this term out. Okay, then 40 divided by this term, 40 divided by 7 into 10 to the 4 of 2, then into 0.12 ln of. So therefore what we can do now, you can see here, dear students, what you have to do here now. So 40, you can see here now how to do the calculations. 40, then 40 divided by what we can do, 40 divided by 7 into 10 to the 4 of 2 into what we can write, 0.12. So what is the answer? What is the answer? Is the, you can make 0.47. So you can make it here, you can mark it as a 0.74. Okay, once you done the 0.74, right, what we can do here now, what we can 0.72. so therefore what we can do, that ln of this thing is the right ln, you can take it at right side now. So therefore what I can write, V2 divided by 0.12, already you know the 0.476, right? When we are going to take ln at right side, then what happens? This becomes e to the power of 0.476. Then what is the value of this one? That you can see here now. Now what will happen now? V2 is equal to, what I can write now, V2 is equal to 0.12 multiplied with what? E to the power of what? 0.476. So this is the same thing you need to substitute here now, that you can see here now. Okay, so now what is the value now? So therefore V2 is equal to 0.2 into what is the value of E? You can see here now where it is, shift E to the 4, what, how much it is? 0.476. What is the value of this? 0. Sorry, here it is what? 0.1, right? See, one second. 0. It is not 0.12, it is not 2, 0.12. Okay, 0.12, that you can see here, dear students. 0.12 multiplied with 0.12, then into e to the power of what? 0.476. Then what is the value? You are going to get 0.193. So V2 is equal to 0.193. Hence second determination also done. Okay, fine. Now next third one. Okay, next. So once it's done, we need to calculate the heat transfer in each processes. Okay, in the first process he has given, in the when it comes to first process, right, first process, what is that first process? He has given heat for first process is equal to, that we can call it as a heat process, for heat first process q1, I will write it here now. How much he has given? 40 kilojoules. Okay, then at again heat, the expansion will takes place at process 2, but there is no heat transfer at all, hence that is equal to kilojoules. That's second process. Third process, isothermal, sorry, compression, but isothermal compression I need to calculate, so that I will tell q3 is equal to how much I need to calculate. Then fourth one, again adiabatic compression, then q4 is equal to 0. So but we can see at all the data, but only unknown is what? q3 here. Now how to calculate that q3? We know the equations. So efficiency is equal to 1 minus heat supplied, you can call heat during compression, or you can call it as a q3 sorry, q3 divided by q4 also you can write, or else heat rejection. 1 minute, you formula you can write your visha, so that you can see here now. So now, so formula is equal to qc is equal to 1 minus heat rejected divided by heat supply. Okay, so what is efficiency of the Carnot engine? He has given already. What is, how much it is? 50%. That 50% means what? 50 divided by 100, it will be 50 divided by 100, it will be how much? 0.5. The same thing I will write it here now. So 0.5 is equal to 1. What is heat supplied? He has given 1 minus heat supplied is equal to how much he has given? 40. So that I will write it here 40, but QR is I don't know, I will write it here QR. So therefore what I can write now? 0.5 is equal to 1 into 40, that means what? 40 minus QR, so I will write it here QR divided by 40. Now I will do simplification now. 0.5 into 40 is equal to 40 minus QR. Then do substitution. 0.5 into 40 is 20 is equal to 40 minus QR. So therefore what I can do now? 20. So therefore 20 minus 40 is equal to minus QR. So 20 minus 40 is nothing but what? Minus 20 is equal to minus QR. Minus will get cancelled. Then QR, how much you are going to get? QR is equal to 20 kilojoules. That means what? Heat rejection during third processes. Okay, so that is nothing but what? Minus 20 kilojoules. Right? So heat is getting rejected from the isothermal compression. If it is getting rejected, we know already heat supplied to the system is positive and heat rejected from system to the surrounding is negative, but heat is getting rejected here, hence it is a minus. Okay, heat transfer during process 1 to 2, while heat is supplied at 1 to 2, whereas heat is getting rejected at 3 to 4. So therefore what is the processes now? As I told, during isothermal process, what is the heat transfer? 40 kilojoules he has given, but during adiabatic expansion there is no heat transfer, hence Q equal to 0. But during isothermal compression, heat is getting rejected. That heat rejection is how much? You have already calculated, that is minus 20 kilojoules per minus 20 kilojoules. In adiabatic compression, there is no heat transfer, hence the heat transfer value is 0. This is how to solve the Carnot engine problem. I hope you understood, dear students. Okay, so dear students, here I request you, please do subscribe my channel, like and do comment and support me. Okay, for more videos please keep on watch my YouTube videos. Thank you.